Good morning, everybody. I hope you've printed out your notes for today on a new skill that we're all going to be learning. Now, many of you may have heard of vectors before in some of your math classes, but you may not remember a lot about it or how we're going to be using it in this class. So, as you know, a lot of the vectors that we use to describe and explain motion in physics are vector quantities. And when you add vectors, it's a lot different from adding scalars because of the directions involved. So, we're going to be taking several days to learn how to deal with vectors in different situations so that we can continue with our description of motion in kinematics. All right, so what is vector addition? Vector addition is simply the addition of two or more vector quantities, either graphically, which we will be doing, or mathematically. Now, when you add two or more vectors together, the answer that you get is called the resultant, because it is the result of adding the vectors. Okay, it's the vector sum. Now, in order to see how we're going to deal with vectors, we need to know how to represent them properly. And there's two ways. You can represent a vector mathematically by looking at the magnitude with a number that represents its size, and you can look at the direction of the vector several different ways, actually. It depends on what type of directional system you're using. For example, in these vectors that I've listed right here, and we need to put their little vector symbols on top since the word processor won't do that. I have no way to do that with my word processor. 6 newtons, 3 meters per second, 10 newtons, 20 meters per second, 120 newtons, 30 meters per second. Those are all the magnitudes of these vectors because they tell you how big they are in a particular unit. The direction is shown differently in some of these vectors. Directions can be as simple as positive and negative. For example, forward and opposite of forward, the other direction. They can be as simple as an axial direction in a Cartesian system. Negative 10 newtons or 10 newtons along the negative x-axis. In other words, that way. Okay? 20 meters per second in the positive y direction. That way. Because as you know, if we look at a Cartesian system, we have positive x, positive y, negative x, and negative y. Now, what's the funny little hat or chevron I'm putting on top? That indicates to a person that that is not 20 meters per second times y. That is 20 meters per second in the positive y direction. So the hat makes that mean an axial direction, okay, instead of a variable, because we don't want to confuse the two. Also, you could indicate direction using cardinal systems. North, south, and east, west, like due north, due south, due east, due west. In other words, along one of the axes. Or you could be between two axes. You could be 10 degrees north of the west axis. Okay? If we have the cardinal system, standard convention, north is straight up, south is down the paper, east is to the right, west is to the left. So this is the Cartesian system, and this is the cardinal system. Okay? So Cartesian directions, cardinal directions. Got it? All right, so the point is we have to represent the vector mathematically with a magnitude and a direction of some type. Okay. Now, how are we going to be adding mathematical vectors? What are we going to be doing? What math process? Well, it depends on the orientation of the vectors themselves. Are they parallel? Are they perpendicular? Are they neither parallel nor perpendicular to each other? We'll be looking at these situations, in which case you might be adding or subtracting. You might be using the Pythagorean theorem. Who knows? We'll take a look at it. However, before we get into that, we're going to look at also how to represent vectors graphically. That means with a picture. Now, how can you represent a vector with a picture? Well, you got to have something that will show how big it is and something that shows the direction it points. And one item that you can draw that shows both is an arrow. Arrows can show magnitude by simply how long you draw them. The longer the arrow you draw, the bigger the vector represented. Arrows also point. You can point them all different ways, okay? So arrows are very good for representing vectors graphically. Now, here's the fun part. How do you add arrows? How do you do that? They're pictures. How do you add them? Well, there's a number of rules we go by. So let's take a look at them. Rules for adding vectors that are arrows. First, and you better memorize this. That's why I'm going to use red now. In fact, I'm using 3 colors today just so you know, because it helps differentiate. I'm using red, blue, and green. But when you have 2 vectors that you're going to add together, say vector A and a vector B, you place them tip to tail. You place them tip to tail, just like I've done here. I've placed the tip of vector B on the tail of vector A. All right? Now, could you put them the other way? Could you have brought vector B over here and put the tip of A on the tail of B? Yes, of course, you could do that. Because of that property in algebra, I can't remember, I think it's the commutative property, or maybe it's the associative. I don't remember which one. But the one that says A plus B is the same thing as B plus A. So it doesn't matter which order you add them in, or which order you place them tip to tail, as long as they are tip to tail and you haven't changed their directions. Remember, changing the size of the arrow or the direction the arrow points is changing the given information, and we can't do that. All right, look at these 2 arrows. If this is vector A and this is vector B, and they're perpendicular to each other, I can still place them tip to tail, and it doesn't matter which tip I put on which tail. I'm still going to get the same answer, okay? As long as they are tip to tail. All right, now, so that's how you stick them together to add them. But what about the resultant? What about the answer? Okay, well, watch this. This is kind of cool. The resultant is also a vector and therefore should be represented by an arrow as well. When we draw the resultant, we draw it tail to tail and tip to tip between the free ends of the original given vectors. For example, here I have a free tail and a free tip because we already glued these 2 together. Here I have a free tail and a free tip because we glued these together right here. So, to draw the resultant, we simply go tail to tail, tip to tip, and there's the resultant. And if you had added them the other way, tail to tail, tip to tip, you still get the same resultant, okay? It's still the same length and still points the same direction from start to finish. So it's like maybe you started at camp, you walked one displacement, you rested for a little bit, then you walked another shorter displacement and you ended up here. So your resultant arrow should point from start to to end, not from end to start. So that's why we have this rule, tail to tail, tip to tip, so that this resultant does point in the proper direction, okay? It has to point in the proper direction. Look right here. If we started right here, we walked this way, then we turned and we walked this way and we ended here, tail to tail, tip to tip, the resultant points this way. And it doesn't matter if we put the other tip on the other tail. It's still going to give us the same answer. Tail to tail, tip to tip, we get a resultant of the same magnitude and the same direction. We must follow these two rules every single time without fail. Okay. So that's how we're going to be adding them graphically. Now, let's look and see what kind of situations we're going to be adding vectors in. Okay, you need to go to your second page now. It should look like this one. Okay, let me get that out of the way. All right, so there's three possible situations. The vectors you're adding might be, and that's spelled wrong, there's supposed to be two L's there, sorry, collinear. Okay, collinear. That means they point either the same direction or they point opposite directions. In other words, they're parallel. Okay, so if you want to write that out there somewhere, that means they're parallel. Another situation in which we could be adding vectors is if they're perpendicular, like that. Another situation we could have is if they're non-perpendicular, that is, they're neither parallel nor perpendicular, but maybe they point at weird angles to each other. Okay, so if you put these two tip to tail, you would not get something that you would for these that's easier to handle. This is much more different. Now, we are actually going to be working with the first two. All right, I do the third one in AP Physics. All right, in here we look at the first two. So now, let's start with collinear vectors. Collinear vectors are vectors that lie along the same line, okay? So, the math process we're going to use is either to add them or subtract them to signify the direction, and the resultant will be collinear to the two vectors you added also. Now, for our purposes, if it's okay with you guys, we're going to forego using units right now. We're just going to deal with pure math, if that's okay. Then we'll add in some physics with units in a little bit. But for right now, let's just work with the math. So let's suppose we have 7 units in the positive x direction. Put a little chevron on that because those are supposed to be axial directions. In fact, on all of these, there's supposed to be a little chevron, but just like the vector symbol, I can't put chevrons on there with my word processor either. All right, so just go ahead and put little chevrons on all those axial directions. All right, so we are using the Cartesian system here. Look what this says. We've got 7 units in the positive x direction, so let's draw one. 1, 2, 3, 4, 5, 6, 7. We'll let each square be a unit, and this is vector A. I'm going to use blue for vector A. And I'm going to use green for vector B, and it's 4 squares in the positive x direction. Okay? All right, now, if we want to add these together, graphically, we have to place them tip to tail. So we would move them 1, 2, 3, 4, 5, 6, 7. And I'm going to slide this one back. Remember, we can't change their magnitudes or their given directions, but we have to place them tip to tail. So we just sort of slide them along our paper until they meet. There we go. There's A. And there's B. Now, the resultant, once we have these drawn tip to tail, the resultant is drawn between the free ends. So, tail to tail, tip to tip, there's the resultant. And as you can see, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 squares in the positive x direction. Okay? Now, how would we show that mathematically? Oh, that's not too difficult. We would say R equals the vector sum of A and B. That's how we write vector sum. No matter what directions they point, we always write this as a vector sum. Even though the math might be a little different, we still write it like this. All right? So now, we're going to say A is 7 in the positive x direction, plus B in the positive, I guess I really need to have, there we go. Now we get it. 4 in the positive x direction. Now notice we can factor out the direction because it's the same for each. So we get 7 plus 4 in the positive x direction. So R is going to be 11 units in the positive x direction. Boom. There we go. That's how we do it mathematically. Okay? That's no big deal, is it? All right? So, why don't you stop the video at the moment, and why don't you try doing this one yourself, okay? Except do notice that this is the positive y direction, which points up the page, just like in math class, all right? So why don't you stop the video, try doing this one both graphically and mathematically, and then come back and see if you got it. Bam! Look at that. Did you get it? I hope so, because these are fairly simple compared to some that we will be doing. All right? So that's not so bad, is it? Tip to tail, and then the resultant is tail to tail, tip to tip between the free ends that we didn't glue together. And we count the squares, we get 14 in the positive y direction. Then the math would look like this. Okay? Formula, numbers plugged in, and answer with magnitude, although there's no unit, and direction. Okay? All right. Now, let's look at a slightly different collinear situation. Uh-oh, look at this. All right. All right, we've got vector A and vector B. Again, I'm still going to use blue for A and green for B. We're using the x-axis this time. So I've got, again, 7 units in the positive x direction. So 1, 2, 3, 4, 5, 6, 7. There it is. Now I've got 4 units in the negative x direction. It points like this now. Oh dear. How in the world am I going to put those tip to tail? Well, it's actually not that difficult, guys. Remember, we can slide this around anywhere we want as long as it stays 4 squares long and continues to point to the left. We can't change the magnitude or direction. So look what I'm going to do. I'm going to redraw A right here, 7 units in the positive x direction. And now I'm going to take B and I'm going to slide it until its tip is on the tail of A. Aha! They overlap. In fact, where they overlap, you've got a positive unit and a negative unit. They cancel out. So what's left to act as the resultant? Remember, we glued these 2 ends together. Here's the free tail. Here's the free tip. Tail to tail, tip to tip. In other words, basically, we're saying that the part of A that's not canceled out by B becomes the resultant. Does that make sense? I hope so. So now, how are we going to show this one mathematically? Oops, almost forgot. 4 units. No, not 4 units. 3 units, isn't it? I can't count today. Okay, so it's 3 units in the positive x direction. There we go. Now, let's show the same thing mathematically. Now, I want you to notice how I write my formula. R, the resultant vector, still equals the sum of A and B, even though mathematically we're not going to be actually adding unless you consider the fact that you're adding a negative. That would work, okay? So I'm going to say R equals 7 units in the positive x direction plus 4 units in the negative x direction. I want you to notice the x hat is common to both. So now if we factor that out, we get 7 plus a negative 4, which is the same thing as minus. So we end up with 3 units in the positive x direction, just like we got in our picture. Okay? Not bad, was it? Okay, so now here's what I want you guys to do. You guys try the same thing with this one, but notice you have a positive y hat and a negative y hat. So try that one, just pause the video, try this one yourself, and then come back and see if you got it right, okay? I'll give you a few minutes to do that. Like magic, isn't it? It appeared. Okay, so I got a diagram that looked like this, and these 4 squares cancel out, and that leaves these 6 squares to be the resultant. So the resultant does point in the positive y direction, tail to tail, tip to tip, between the 2 ends that we did not glue together. Here's the ends that we glued, okay? All right, so that's collinear vector addition. And you are going to be working on an assignment where you're going to be practicing that. All right, thanks guys, bye.